Good morning, everybody. First, we're really excited about the acquisition of this new technology that we're going to present to you today. So we made this acquisition a few weeks ago, or finalized that acquisition a few weeks ago. But I want to give a short introduction about what's our reasoning, what is our technology today. So Altair at a glance, a little business update to Altair. So we are like around for 32 years. There's about over 2,000 employees, 5,000 customers, and we have a worldwide network of offices where we do distribution of software, but also software development. So our development is not just in one place, so we are all over the globe. And our products are marketed under 4 different brands. So the most known is probably HyperWorks, where you find the technologies like HyperMesh and OptiStuck. We are branding it today as a multi-physics optimization platform for CAE engineers. So it's mostly at high-end organizations, organizations that do a lot of CAE, like automotive OEMs and aerospace companies, but also other industries. Later, around the design technology and OptiStuck optimization, we developed the concept of simulation-driven design. And this has been branded under Solid Thinking, where you find products like Inspire, and also the math products like Activate and Compose that are branded under the Solid Thinking brand. And then last year, or two years ago, we did an acquisition in the space of the Internet of Things that is now marketed under the brand of SmartWorks that will do the digital twin technology and so on. I'm not sure how can I get rid of this thing. Okay. And then, of course, for computation, for high performance computing and cloud computing, we have the brand of PBS Works, which started actually in the early 2000s with the acquisition of PBS from NASA. All our software technology is marketed under a units-based subscription model. You probably know the HyperWorks units. This year in September, we introduced the Solid Thinking units. So we have like 2-tier units where you license our product. So you buy a pool of units, and then basically the software application draws a number of units. When you're done with using the software applications, the units go back in the pool, and somebody else can use the units, or you can open another software product. And the Solid Thinking units are focused on the Inspire products and the math solution products, while the HyperWorks units allow you access to all the technology that is being developed at Altair, plus a number of applications from our partners. So with the HyperWorks units, you have access to about 150 software titles. That is a lot of value that you get with those units. Our vision is to transform design and decision making by applying simulation, machine learning, and optimization. And from that perspective, you really have to see that new technology that Ken is going to introduce to you. When we saw that technology, we were really excited to find a piece of technology like this that really helps to accelerate the use of simulation in the decision making and during the design process. Our software development focus is on mixed fidelity multi-physics development. So aside from typical finite element solvers, we also develop 1D solvers. We develop different couplings. We use data-driven analysis, machine learning in our simulations. And this is really where SimSolid fits in, giving more technology for modeling structures. Computational performance is really important to us. So all our solvers are highly parallelized. In this day and age, we have CFD technology that's based on GPUs and so on. And you will see actually with SimSolid that that really the computation performance is quite amazing, and is really cutting down the entire process of setting up a model and getting a result. And then, of course, pervasive optimization. From the beginning, we built our technology around optimization, and we will also put optimization together with SimSolid at some point. So we cover the entire portfolio of physics, from system simulation, structural, thermal, fluids, manufacturing, electromagnetics, simulation. We have all these different solver technologies that are connected through some solver coupling, but the main idea of using simulation in the design process, designing products, is the connection through optimization. So we will build optimization into all these tools to do multiphysics optimization to more or less a degree. So in OptiStart, for example, you have a complete integration of the optimization with the physics, and you can use hyperstudy also to do optimization for other nonlinear physics. So we'll see. You see here in this pattern that we have different software titles for different applications. OptiStart for structural and linear, OptiSolve for motion, FluidDyna for fluids, MotionSolve for multibody, Flux and Fake for electromagnetism, Inspire for manufacturing simulation, and Activate for system simulation. So bringing all these physics together, you can do different couplings, but use them as a standalone product. So our solver technology really covers the entire physics that you need to design a product, and it's connected with design optimization, machine learning. And for us, when we saw SimSolid first, it was really that SimSolid is really a good fit in structural simulation during the design process for designers to give easy access, and also in the context of Inspire, where we take OptiStart technology and manufacturing technology and bring it to the designer, and we will integrate to do an integration further down the line. Ken will talk a little bit about the business model. So it was for us really an exciting that we could get together with SimSolid people and acquire SimSolid. So we made the announcement in October at our ATC in Paris. So it's really SimSolid is working off CAD assemblies and provides really fast and accurate robust structural optimization with out the requirement of geometry simplification and cleanup. Victor, Ken, great people that joined the organization, and together we're going to pour investment into SimSolid and really try to bring a really great solution to you guys so that you can iterate faster and develop innovative designs. So that's about for me. I will hand over to Ken to introduce the technology itself.
Okay, do I have control there? Yeah, so show my screen. How's that? Can you guys see my screen? Good.
Yes.
So yeah, so I'm Ken Welch. I'm one of the two co-founders, as we mentioned. You know, we started SimSolid, 3 or 4 years ago, and when you start a company, you have to think about solving a problem. For us, that problem was what I called the mesh problem. So what was the mesh problem? If you think about analysis is just tough to do, and the reason it's tough is you got to make a mesh, and making that mesh is a very complicated process. It's a very slow process, and you have to learn it's complex to learn how to do it and things like that. Meshing is really a problem in the design process. So if you think about doing design analysis, it's a time limited process. And if you have a very complex, long-winded, hard to use methodology like meshing, it just limits you in analysis. It's funny, when we started the company, we talked to a lot of people, and there was a big disconnect we found in the CAD market. All the CAD guys were talking about, we have this democratize analysis. It's basically got a very nice UI and it's embedded in CAD. And all the users said that stuff doesn't work. And I said, well, how could it, be democratized? It doesn't work. Well, it works great. It just doesn't work on real world problems. And and that's the thing. It typically works on very simple problems. And what analysis has been in the past has been limited to very simple applications. Limits its appeal. So our view was to take a fresh look, and the fresh look is at a very core level. So SimSolid is a new technology. It has a few nice attributes. Number one, it operates directly on the unsimplified CAD geometry. So you don't have to take the geometry and mid-surface it or defeature it and all those kind of things. Just take the original geometry and it tries to work on that. And it doesn't create a mesh. So using the original geometry and not creating a mesh, it eliminates a bulk of the pre-processing time for analysis. The other thing that SimSolid is, it's very high capacity. We tuned it specifically to solve both large assemblies and complex parts. So, take your original form, you don't have to go and break off just one or two parts. You can analyze a large subassembly or a very complicated part directly. Now, it is meshless, but there is, because it's meshless, accuracy is controlled by an adaptive process. So as it solves multiple times, and every time it solves, it looks at the errors in the errors in the solution and locally enriches the equation and resolves. So it's an automatic adaptive process. You can't turn it off. And we said if we're going to be used in design, it's got to be fast. Our target workflow is to give you meaningful results in seconds to minutes. So even a large assembly. So that's a pretty audacious goal. But when we started the company, we said that's the things you really need to have in order to make have an impact with analysis in product design. So I talked about product design. So where does it fit? Well, clearly we think it fits in an area where you're doing rapid design ideation, right? So if you're trying to evolve a design and you want to understand the performance insight early and often, that's SimSolid. So if you look at the classical product development V, we're typically at that front end. We're not a validation tool. So it's really not to say, oh, I want to find the nth degree of stress. I mean, you can drill into stresses, but really the strength of it is using implemented design. The traditional tools are over here in the validation phase. So, in terms of what I always say is that FEA requires geometry adaptation to mesh. You have to change the geometry. Our goal with SimSolid accept it as is. And people say, well, I've heard people say, well, the meshing's the easy part. I say, well, it is easy until you have, an assembly that has both big and small and thick or thin parts, which is very common, or until you have parts that have extreme, geometry detail, like these small holes and fillets and things like that. Or if you have odd phase transitions, like I don't know if you guys can see my cursor, but on the bottom right, that can be problematic for mesh generation. And one of the very topical things today is this, generative design kind of parts, all these lattice parts. These are typically very difficult to mesh. But the number one problem, I think, in terms of doing quick performance simulation is trying to connect different parts together. Parts may look aligned, but mathematically there's a small gap or an overlap, and this can be problematic in terms of, bonding these things together or building connections. One of the founding principles of SimSolid was we came up with a new method to build a connection between parts that can have a little ragged connection that can be overlapped or gapped and things like that. And what we do is we use this connection as part of our criteria on the adaptation. So think about this. If you have two parts together, the stresses are not continuous, but the surface tractions are. So what we do as we evolve the solving, we'll look at the errors, the traction errors, the boundaries, and then locally enrich the equations to minimize those errors. So even though you have a very ragged connection, we can always find a good load path, and this is really one of the true strengths of the system. So let's talk about how it works. I think everybody knows the background of traditional FEA. You typically have a simple region that for 3D is a TET. The degrees of freedom are typically point-wise, and they're, for structural analysis, typically displacement-based. Again, for TETs, 3 degrees of freedom per node is common, and the shape functions are low orders. They're, you know, linear, quadratic, things like that. SimSolid is much different. It doesn't have a region like a TET. The regions can be completely arbitrary. In fact, they can be whole parts. So, and the degrees of freedom are not point-wise. They can be associated to anything, volumes, surfaces, lines, or even point clouds. So there's a lot of versatility in how we can construct the equations. The degrees of freedom are integrals. They're abstract coefficients. They're not physical displacements. And there can be many degrees of freedom, you know, per geometric entity. The shape functions can be an arbitrary class and actually derived on the fly for every single part, which is a little bit unique to our system. But probably one of the most interesting things is this boundary compatibility. Now, you know, if you take a cantilever beam and you fix one end in finite elements, what you're saying is the degrees of freedom, or, you know, the displacements at that end are 0, exactly. You specify exact boundaries of 0. In SimSolid, you don't do that. In SimSolid, when you fix a boundary, what you're really saying is the goal is to have 0 displacement at that boundary. So the boundary compatibility is met approximately. Well, why do we do that? Remember that boundary could be at a support, but it could also be a boundary between parts. And this iteration, this is where we iterate to minimize the error in those goals. So even though we say it's okay to be not exact 0, in the end, it will be engineering 0, right? So that's kind of the methodology there. If you think about accuracy, let's look at traditional FEA. Traditional FEA, a lot of the accuracy is really the decision by the user. You know, you have to decide yourself what the appropriate level of geometric detail is. You have to decide for yourself what type of elements, what type of mesh density, what distribution. You have to decide for yourself, and this is where most people or many people get in trouble, is you have to understand the correct interpretation of the settings. You know, if you look at dynamics especially, there are many, many settings that you can possibly set in traditional methods. And every time you can change the setting, it's an opportunity for error. And we find that, you know, many codes are not that they're running correctly. It's just the user interpretation of the correct settings is not being made. Now, you know, almost all finite elements today can have, you know, automatic adaptation. They can be H or P adaptivity, but typically that's rarely done for assemblies. For us, we have the full geometry detail. You know, there is no elements, no meshing. We have very minimal settings for dynamics or nonlinear, even separating contact with friction. And our solution adaptive is always active. So again, we're trying to build an analysis system for design, and all of these areas here that are in traditional FEA are bottlenecks in design. And you can see that's the reason we went on this route with SimSolid. So just talk briefly about what it does. We wanted to have a system that could run rapidly, but it had to be meaningful. So it does quite a bit for design code. It does linear statics, it does modal, it does nonlinear statics that can be either geometric or material. It does transient dynamics that can be time, frequency, or random response. It does base excitation as well. It can do thermal and thermal stress, and we have things like inertial relief and bulk pretension. Our materials today are isotropic. You can make parts rigid. you know, and we have a simple elastoplastic model. This is an area we can extend quite a bit in the future, but today it is isotropic. And since we really focus on assemblies, we spend a lot of time with connections. We have a rich set of connections that can be bonded, sliding, separating with friction. We can do bolted connections. We can do spot welds, seam welds, and we can even do virtual connections, which are just rigid connections between different faces. So, you know, and we'll show more detail with during the demo. Just to give you a couple ideas on what the capabilities are. First of all, SimSolid only solves solids, so there isn't a shell type element in SimSolid. So here, but we can solve thin structures. Here is a benchmark, and actually it's a pretty severe benchmark. It's a doubly curved, internally pressurized thin wall solid. It's completely clamped at the 3 inlet outlets, and because you clamp that very small, and here you get this displacement hotspot there, and you get a stress distribution like this. Now we solved it as a thin solid, but you know it's using 3D continuum theory. Okay, so and in spite of the fact that you know this is a pretty challenging geometry, we got with our adaptation process, we could get this result directly. We can do bolt tightening, and the bolt tightening is a little bit unique in that it's full 3D. So we have there's some information on our website in terms of the theory that we use, but it's a full 3D representation. We do spot welds. The spot welds can be just applied manually, or you can bring them in from a CSV file. We can do fillet welds, and we can do fillet weld automation. The automation is interesting. We can bring in tubes, you know, tube bodies from the CAD system, and then automatically convert them into welds. So if you have these 3D structures that are common in CAD, you can bring them in and convert them automatically. You can also make the welds manually as well. We do sliding contact. We do bonded contact. We do separating contact. This is nonlinear separating contact. So we do that. This is interesting for us in that it runs fairly fast. I'll show you a demo of that. We can do geometric nonlinear. We don't have linear buckling. We don't have, you know, eigenvalue buckling because it really doesn't make that much sense for assemblies. But you can do geometric nonlinear to see if you have a buckle shape. We can do simple elastoplastic, mild nonlinear, really just for ductile steels, but we can do that and combine it with geometric nonlinear. We can do transient dynamics, and the transient's interesting in that you know, dynamics are really a data problem. You have to store, you know, a result for every time step, and it typically can be quite large. For us, we don't store any of that. We only store our analytic functions, and then we have a way to recover all the data in post. So, you know, and if you look at a typical dynamic simulation, our result footprint is orders of magnitude less than what you see in traditional methods. Maybe a few quick customer applications. This just to show you some typical ways SimSolid is used. Serapid, they're a company in Michigan. They're a very early customer, SolidWorks user. They build these really innovative, they're very cool, vertical chain lift technology. You can see they're quite complex. And you know, they analyze typically the entire assembly, even sometimes with the lifting table, all done with SimSolid. Here is, I think there is a second application. You know, for them, they told me, they said, you know, Ken, honestly, we do an analysis. We didn't use it as much as we'd like in the past because it just was too complicated. With your stuff, we use it every day, and we can look really quickly to understand, you know, as we make design changes, how is the load path changing? So we're, you know, they're not trying to look at detailed stress studies, but they want to say, how is my design evolving, and how is the overall response changing with the design? And you can see here, this is almost an 800-part assembly. They have, you know, many design studies, you know, with different design configurations they're evaluating in SimSolid. Adron Handling is an interesting company. They're in the UK. They make these bespoke manufacturing equipment for automotive. This is an assembly line, a tire handler. So those are actually tires. And this was an analysis they recently did, and they said that, you know, in the past they would have had to done a number of analysis, you know, small, you know, component things, and they had to understand the load paths and all that. They said with SimSolid, they could do this analysis start to finish in, you know, an hour and a half. So they were very happy that, you know, they could get some insight quickly, even on a very complex assembly. And this is another example of theirs. I like this one just because it shows the difference between bonded and separating contact. Now, you know, this is a typical way you would just say, take that plate and bond it to that tube. There's nothing wrong with that, and you'll get this perfectly, you know, connected boundary. But if you have these bolts like that and you make it separating, you'll get a more realistic distribution of the load. And you can see that this typically takes, I think this was about a minute to solve. This was about a minute 20. So it's really not that big of a penalty to turn on separating contact. It does iterate. It's nonlinear, but it's a nice effect to have the ability to turn on. One final application is just some research. Western Ontario University, they're doing some correlation of SimSolid to with respect to high resolution scans of bones. So they're scanning the bone. I think this one up here is this is a hip bone. This is an implant in the shoulder scapula. This is a bite study with a 3D printed test scan. But you can see this one here. It was I think 8.25 million facets of STL. It's a very high resolution scan. And this is something typically you would not want to mesh. In fact, I don't think it'd be practical to mesh, but they were very happy they can get a result through that. And they're doing some great correlation with you know, putting on test scans and testing it. So I think this is an interesting application of really complex geometry. Okay, why don't I see if I can start it up and do a little, let's just try it. Here is the product on our desktop, and this is what you see when you first start. Let's bring in some geometry. Now I can bring in geometry from just a CAD file, you know, CATIA, NX, you know, Parasolid, Step, etc. Or I can also bring it in from a cloud source. This is its Onshape. So I'm just going to grab a model, and I'll grab this one right here. I'm going to do a real quick analysis, but I just want to show you the workflow. So this is a pull-up bar. Let's first just create the connections. Okay, so that creates all the connections. This is about 33 parts. Let's do the analysis. I can do structural, linear, non-linear. I can do modal. I can do transient dynamics. So let's just thermal, etc. Let's do linear. Let me just constrain the back here. Let's just do something quick. And then let's just load the ends here. Maybe something like minus 500 newtons. I don't know. Okay, then I just say go. That's it. So I didn't do anything other than that. It's now solving 1, 2, 3 passes. You know, in fact, that was solve, mesh, iterate. So I can now look at displacements. I think that took about 4 seconds to solve, and I can animate that. I can bookmark that animation. Maybe I'll stop that. Maybe I'll look at, instead of displacements, I'll look at stresses, and I'll bookmark that. Okay. So that's great. That's nice that I can get an analysis very quickly, but I can also do a few more things. Let's just copy that. Let's double click to edit the load. Let's just pick these 2 things and delete them. And let's move the load path. Let's move the load back here. Okay, let's just run that. Now, reanalysis is even faster. I think it took 4 seconds for the first one. That was 2 seconds. And again, that was solving 3 passes. So it solved the pass, looked at errors, locally enriched the equations, resolved, relooked at errors, and iterated. And if I pick the bookmark, it'll go back. You see where it's bold here. This is the first result. So there's the first result. But I can just pick down here, and there's my second result. So I can very quickly between, there's my display shape for load case 2, and there's for load case 1. Okay? And I can do the similar thing for stress. There's stress for load case 1, stress for load case 2. Well, I think that's pretty cool. I mean, I can do a very rapid analysis and assembly. And I can also tweak the values if I want to drill into, you see, more local stress detail and things like that. But really what's the power of the system is you want to understand design change. So let's assume I go back to my CAD system and I grab a different configuration. I could have changed the model in the CAD system or just grab a different configuration altogether. And as I pick this one here, it'll bring in the change geometry. But you see what it happens, it says, it's a, this is new geometry. I'm going to assume it's a design study, a second design study. I'm going to copy down all the boundary conditions and load cases for the first. So everything's ready to go. All I have to do is pick here, and I just pick this and it'll run both load cases. That's load case 1 it's running, and then there's load case 2. Okay, so now I've just run, 2 load cases on 2 different geometric configurations, and I can scan through there the same way. There is load case, or there's geometry 1, and I just pick here, there's geometry 2. You see that the back is a bigger thing. So I can go quickly between geometry 1 and geometry 2. And the same thing for stress. There is stress for 1, there is stress for 2. Back and forth. And again, also for 2, I can look at, load case 2, load case 1. So our workflow, what our workflow is we're trying to say, I want to do it on the real geometry. I don't want to simplify it. I want to make as few assumptions myself as I can and get a result quick. Now, although it came in, there was a few things that happened in the background that made it go fast. One, geometry comes in, we evaluate the geometry. If we see bolts, let's find it as a bolt. And we use that because we want to do a bolt pre-tension later. But also, as we identify bolts, we actually change the connection condition from bonded to sliding. So although it just came in and you just said, connect, it made bonded connections, it made sliding connections, it went through the whole model. So there was a lot of automation behind the scenes that allowed it to build that analysis so quickly. In fact, let's try a second example to maybe drill in a little bit more detail. Let's go to this model. Now this is a little bit bigger model, not much. It's I think 55 parts, and this was a benchmark that we got. It was people were really wanted to understand, can you kind of drill into the detail of a bolded connection, right? So here is the initial. It's a simple pull down here and just constrain the back, and and it looks like this. So it's a very simple load case, right? Now, here's the challenge. So this is the default load case, although we've made this is a 4-pass iteration. So I boost the resolution just a bit. But if you look at the display shape, it assumes that this big beam is bonded to this big beam. So it's perfectly bonded. Well, that's fine. That gives you the overall load path. But if you were really concerned about the stresses and the bolts, it's probably not a good idea because the stresses are being carried by that big beam connected to the big beam. Okay, so if I want to get a little more detail in the joint, what would I do? Well, one thing I could do is I could eliminate that bonded connection there. So the way I do that is I just pick here, I say review part connection. I look here and there's a connection for that part, and I know that one and this one, those are my 2 bonded connections there. The red indicates bonded. So if I want to edit that, I just say edit the contact condition for structural analysis 2. And instead of bonded, let's make it separating with friction coefficient of 0.1. Okay, for structural 2, separating contact, okay, close. That's all I got to do. Now let's run structural 2. Now this is, I got a 55 part assembly and I'm doing 4 passes and I'm also doing nonlinear contact. So that ran, you know, I don't know, how long did it take? It took 7 seconds to do. It's fairly fast. But if I go and look at my results here, now again, I picked my bookmark. You see it's bold, so this is the first load case. If I pick down here, you can see exaggeration, then I am starting to separate there, right? So I do have separation of display shape. And if I look at, again, at the stress state, here's the stress state of the bolts for the first one. Here's the stress state for the second one. So now I'm getting, because in the moment, I'm getting, you know, the stresses in those bolts as I would expect. I can do one more level of detail, though, pretty easily. Let's copy this down. Let's copy here, and here let's actually, you know, pre-tension those bolts. So the way I would do that, I just pick the nut. I could just pick these. Let's just pick those 4. And now I just specify a thread pitch, and I have a couple of methods I can use to pre-tension. I can do a turn of a nut, so, you know, quarter turn or something like that. I can do a torque and friction value, or I can just do a target axial load. So let's just do a target axial load. Let's say I want to, you know, stress these to a target load of 3,000 newtons. I can do that. And now I can just run this. So this is 4 adaptive passes, nonlinear contact, and bolt preload. So it's quite a bit, you know, going on, but it gives me a little bit, I'm going from a kind of a general view to a more detailed view on my my result there. So here is the result. There's my display shape 1, display shape load case 2, display shape load case 3. You see the bolt pretension pulling it down a little bit. And again, for the stresses, and there's the stresses with bolt pretension. So look, what we try to do with SimSolid is, it's a design tool. It's not a validation tool. Its primary intent is doing rapid design iterations, but we want to give you meaningful performance insight quickly. So meaningful performance insight quickly on large assemblies or complex parts. Now, quickly, you know, here it was a few seconds. Many parts are like that, you know, seconds to minutes. You know, bigger models can be, you know, minutes, you know, 5-10 minutes. But the ones that are solved like these lattices in 10 minutes, that might be hours someplace else. So we're really still trying to give you meaningful results quickly. And also, you know, it's not just the solve time we're talking about. We're trying to reduce the workflow time of creating the mesh, tweaking the geometry. You know, we're trying to, the goal is to work directly off the design geometry. Okay, why don't I stop there? Let me go make a few other comments. You know, it's been very exciting for us being acquired by Altair. I think that it really allows us to push this technology in a lot of different ways. I mean, there's a lot of great technology at Altair that I look forward to coupling to. So there's just a lot more things that we can do. Today, it works, you know, our product, it was historically sold as a fixed seat license. And that's the way it is right now. But we're in the process of integrating to Altair's HyperWorks Units licensing. So, and we expect to release that later this year. So, you know, if you want to try it, you can go to the Altair website, go to altair.com/SimSolid. There's a free trial. It's a 60-day free trial. You can get it right now. And it has all the features. And we'll leave the free trial there until we release this HyperWorks unit version later this year. So I guess I'll stop there and open to questions. I would just like to say we're excited about working, you know, in the Altair environment. I think what you see today is just the start of what we can achieve, you know, going forward.